Hi, good morning and welcome to the webinar in which we're going to be talking about knowledge graphs and in particular the power of graph-based search within this context. And thanks very much for making it this morning. So I'll just introduce myself quickly. My name is Petra Selmer and I'm a member of the Query Languages Standards and Research Group. And what we essentially do in this group is identify, design and then specify new features for Cypher. These are features that will eventually make it into the query language. And on the back of this, what we actually do is we write many documents detailing, for instance, the syntax, semantics, i.e. the behavior, and so on of these new features. And what we also do is collaborate with academic partners so that we actually, what this actually means is that we are then at the forefront of graph querying developments in general. So just in front of you now is the outline for this morning's talk, and what I'm going to start with is the property graph data model. And I realize probably most of you are very familiar with this, but because it's very foundational to the rest of the presentation, I'll just introduce it briefly for those of you who are maybe not so familiar with it. I'll then actually talk a little bit about Neo4j itself, and then we'll actually dive into the meat of this session, aka knowledge graphs. I'll begin by setting the scene a bit, talking about the background. Also, my particular take on what a knowledge graph is. What is it? How is it used? Why do we need it? That sort of thing. Also, how we envisage using it within Neo4j, and various tools and techniques you can use to actually manage your knowledge graph and how to basically take it forwards into the future and how to use it effectively. And then the last part of the talk will be about graph search through Cypher. That will introduce a small introduction to Cypher for those of you who perhaps are not familiar with it on a day-to-day basis, and after that I'll be going on to various extensions that the Query Languages Standards and Research Group are looking into adding to Cypher in the future. So I shall begin quickly with the property graph data model refreshment. So the idea here is that obviously the underlying construct is a graph, and it consists of three main facets, if you like. So the first one is a node, and this essentially represents entities of interest within a domain. So for example, a node can be a person, a node can be a building, a node can be a vehicle, these sorts of things. That's also analogous to those of you who come from a mathematical background to the notion of a vertex. So it's a synonymous term. The next facet is a relationship, and that essentially is the connection between your nodes. And essentially what relationships do is, by their very nature, is to add structure to the graph, and they provide semantic context for your nodes. So not only do you have a node which is labeled as a person, you can also see that this particular person actually lives, exemplified by a lives relationship, in a building, where the building is perhaps another node with a label of building on it. And by actually bringing relationships like this to the fore, it actually gives much more structure and semantic meaning to your graph. The final facet is properties, and essentially these are just essentially the actual data items, the attributes, if you like, of your nodes and relationships. And these are represented and stored as key value pairs, which actually represent the name of your property. So perhaps a property literally called name, and value would then be the value of that property. So for example, something like John or Anne or something like that. So it's showing a bit more information here. So a node may have 0 or more labels, and by this we actually mean that a node can actually, depending on the amount of labels you assign to a node, this gives it even more richer semantic context. So for example, a node can be both a person and a teacher, or you can actually have a node that's just a person only, because maybe you don't have any other information about that particular person. We also do allow the fact that a node may not necessarily need to have labels, but we do find that this is quite an odd thing to do. And we actually see it very rarely in practice. Moving on to relationships, relationship absolutely has got to have one and only one type, and also direction. So we actually have this is basically a directed graph. And things like a type could be something like knows, likes, etc. And then furthermore, and this is what I was talking about a bit earlier, a node or a relationship may have 0 or more properties. So again, this is an example. So a node, for example, could be a person node. And in fact, if you see the diagram on the right-hand side, we see that there are 3 nodes in there. And if we just focus on the leftmost one, we see that that node has got a person label. Also, he loves Anne. So he loves the node on the right-hand side. He also drives a car down on the bottom. And there are also various outgoing and incoming relationships. And we can actually see that there are a number of properties associated with this person. So we see that the name is Dan, we see that he was born in 1970, etc., etc. We actually have noticed, in contrast to the label story, that nodes and relationships frequently, or not frequently rather, may sometimes not have any properties. And this is actually perfectly okay, because there are actually applications that use the property graph model to model a the topology. So for example, like a water flow network or something where you have junctions and pipes and things like that. And in that case, maybe properties are not that relevant or useful. But in general, we actually do notice that by and large, most nodes will have properties and most relationships as well. So I think what I'm hoping is that the idea that's coming across here is that you can very quickly get a very rich description of your domain by using a graph. So in this picture over here, I've not explained anything to you. What you're actually able to very quickly see just by looking at this, graphs are obviously a very visual construct. You can very easily see what the entities of interest are, how the information flows, and you can very, very quickly see what the context is all about. Just diving into some use cases that we're starting to see crop up more and more in industry in particular are things like impact analysis, so which are the most dependent upon components in your data center. For example, logistics and routing, so what's the most efficient way of, say, delivering a parcel delivery or something like that, recommendations, access control, etc. I'm actually going to talk a little bit more about those later on in the talk. And I just wanted to round off this section with a couple of very well-known use cases. They actually are both using NEO under the hood. And the first one is NASA. And essentially what they are doing is using NEO to store all their mission history. And essentially this encompasses knowledge of every launch that they've actually undertaken over the past few decades. And what they're actually doing is, in their current research and the current missions that they're planning for, what they can actually do is trace back to situations where various problems that they're encountering now actually occurred in the past. And what this allows them to do is just to see very quickly, through root cause analysis, what went wrong on those missions that were similar to missions that they're perhaps planning today, and also perhaps to see what alternative configurations for components and things like that are. And previously, it used to take them a very long time to actually search through their old system using tables and records. So you can imagine if you're going back all the way to the 70s, you know, this would have taken quite a lot of digital archaeology and forensics. What they actually can do now is find that information incredibly quickly. And the takeaway actually is that this apparently has saved them about 2 years worth of research into the decision-making process. That's actually really, really exciting. The second case, I'm sure most of you heard a lot about this last year in particular, Panama Papers, and as you can see, they won the Pulitzer Prize last year. And this essentially was tracking where money was flowing. And as you recall, this was the leaked data from Mossack Fonseca, in which various organizations and individuals were evading tax. And as you probably recall, many newsworthy items and investigations came out of there. And Paradise Papers was kind of the sequel to this, to Panama Papers, and it continued in the same vein. And essentially what's happening and what's still ongoing is that the original Panama Papers graph, if you like, which was then enriched subsequently with the Paradise Papers information, is still being added to, and I'm sure over the years we'll actually see many more stories come out of there. But anyway, the idea with both of these applications was that the core underlying technology was Neo4j, graph database, and the idea was that even non-technical people could very easily get an idea of how what was happening, how things are related, tracking things through searching, etc. So just I'm going to just spend the next few slides talking a little bit about Neo4j in particular. So we like to now consider ourselves the graph platform for connected data. And essentially lying at the heart of all of this is a native graph property database. And what this essentially means is that we've developed the database from the ground up to handle graphs natively. So we don't actually sit atop any other layers that may actually cause indirections and non-graph operations to prevail over the graph operation. And what this basically means is that we store nodes and properties and relationships as first-class citizens, and this actually makes things very, very quick, very, very fast, queries execute very quickly. We also ensure that we comply with ACID, so that essentially means that your data is safe. So once you commit the data to your to the database, it is written and it's not ever lost or corrupted. And we also have always tried to ensure that the product is easy to use. So we very much began by looking at the transactional graphs. So if you look at the triangle in the image, we began by actually concentrating on developers and DevOps and transactional graphs. And what actually has happened over the last year or so is we've started to expand this picture. So we are moving away now just from solely concentrating on real-time OLTP and moving over into two other spheres, if you like. So on the left-hand side, you can see we're actually also now considering people such as data scientists, and obviously these are the guys who use graph algorithms to perform very complex analysis. And essentially what they're doing is, or at least what this group of people are doing, is looking at the graph as a global structure and actually finding substructures within that. So this is unlike the transactional graph story, where generally only bits of the graph are modified or viewed at any one point in time. And then of course on the right-hand side, we also are now also spending much more time catering for the business user. So this essentially is that they can get a very high-level overview of what's happening. So we're bringing in loads of visualization tools and techniques to bring to bear on that. Just to dive a little bit more deeply into the graph platform, as you can see in the circle, the Neo4j cylinder that you can see in the middle, that's actually our database. And all the bits around it are now considered our extended graph platform. So as you can see, there's actually a lot more going on now. So we essentially, to reiterate, we're trying to drive the use of connected data beyond just the developer area. And I don't mean just the developer area, but we're just trying to expand the focus there. So we're shifting focus away from them to also include other facets of the organizational enterprise, such as business intelligence and, as I say, the analysts. So areas such as graph visualization and graph analytics, and these include algorithms such as cluster detection, PageRank, all those sorts of things, are now taking much more of a prominent role. And the idea essentially is that non-developer personnel can actually get a much more robust view of the data, and that actually everything evolves in that way. So I'm now coming to the actual meat of the talk, and knowledge graphs. And first I'll set the scene a bit by talking about the background a bit. And so initially, a few slides back, as you may recall, I was showing you a few use cases. So I'll just talk a little bit more about them. So in here, you actually see loads of things that probably most of you are aware of. They've actually been becoming more and more prevalent over the last few years. So for example, we've got recommendations, and these are generally undertaken by retailers. We've got fraud detections. This is where people are able to detect the flow of money, and they're able to keep an eye on any suspicious patterns emerging and then act in real time upon that. That, whoops, it looks like, there's some fraudulent activity occurring in Nottingham, say, or something like that. As I mentioned before, the network case is actually a very, very popular one, mostly with root cause analysis, and also, as I said, seeing what the most dependent upon component in a data center is, for example. So, for instance, if you have a component that most of your services rely on, and should that go bang one day, very sadly, what would the effect be, right? So it's also basically a way of actually minimizing risk in that particular sector. What's actually not on this diagram is a sector I'm very interested in myself, having come from that area, and that's healthcare, pharmaceuticals, and bioinformatics. So essentially, pharmaceutical industries are now looking using graphs as a way to actually help them reposition and repurpose drugs, for example, and to also get other discoveries coming out of their data. And bioinformatics applications, for example, would be to actually model and analyze protein interactions. So these areas are actually growing and growing a lot. And so I've seen a few in industry, but certainly a lot in academia. It's certainly become quite popular to use graph databases to actually feed that, because this data essentially is very graphy. Right, so to take a bit of a step back, so what's the problem we're actually looking at? So if you just look at the slide, you're probably thinking to yourself, actually, none of these problems are really new. We've actually had these issues bubbling away for the last few decades. Well, it's only really now that we actually are starting to find solutions, or maybe partial solutions, to these problems. So essentially what we have here is the fact that any healthy business obviously needs to grow and evolve. And obviously this process presents challenges. And certainly the point I can resonate with a lot is the last one, which is the aging infrastructures and siloed information, where all of these different silos spread across an organization may actually contain really great nuggets of information. And the problem is, of course, you actually can't get to it. And that's actually what knowledge graphs seek to actually solve. So the negative consequences of having siloed information, or at least information you can't actually act upon, is as exemplified by the list shown. And actually, I would say that the biggest one, I think, is the one I highlighted, which is essentially you don't really know what you don't know. This is one of those huge uncertain things in life in general. And the idea is that graphs are actually a great way to bring those sorts of gaps into the light, and basically leading through to new insights being made. And obviously as well, it's obviously never a good thing to have bad information to be spread out through a company. And also it would be a huge pity if market conditions change to the point that a great opportunity makes itself known, but that an organization is unable to act to it just simply because they don't have the information to hand, or they're not able to act on it quickly enough. So just to take a very much an eagle-eyed view on knowledge graphs. So essentially I've sketched out a picture below what this looks like. So if you have a look at the diagram, there are a number of silos in there. So we can actually see there's a consumer data database, product data database, etc., etc. So each one of these departments or sections of a company, if you like, has got its own data. And the idea is that the knowledge graph, if you look on the top half of the image, actually joins all of this data together. And in this way, you actually get a cross-sectional view. So I'm now going to give you my take on what I think knowledge graph is and why it's a useful thing. So I'm going to actually walk you through a few steps. The idea is to actually enrich graphs with more and more data, raw or derived over time. And what this actually will give you is it will result in a graph that has more detail than the original graph, more context, i.e. maybe there are richer connections that have now come to the fore or that have been added, more truth. By truth, by the way, I mean that the data is correct. So maybe the original data was not 100% verified, maybe it was incomplete. But anyway, the idea is that as the graph evolves by being enriched, the processes actually augment the data so that it becomes more and more correct. And this very much is driven by relationships as a first-class citizen. And because of that, we now actually have a graph that is more intelligent than the original one, and also furthermore has much better and more fine-grained semantics. Now, being in this position, what this means is that this enriched graph, and bearing in mind, of course, that this is probably could come over quite a few iterations, the idea is that eventually your actual domain, i.e. what is important to you, is actually captured much more precisely. And one thing I'd like to actually bring out here is that property graph data model does have an optional schema. So what that means is when you begin with your initial graph, you may not be quite sure of what your data model looks like, maybe just experimenting or exploring. And the idea is that over time, as you get more and more data, as your graph becomes more and more rich, you can actually, various invariants in your model may start to make themselves known. So you may actually start to see that people can only ever be connected to buildings or vehicles or other people, but that there's no way, there's no sense in connecting people, say, to a bathroom or something like that. Obviously, it's not a great example, but you get the idea. So as your graph gets richer and richer, you actually start to see what parts of your data model you want to start locking down. And then in which case, this is where you can start bringing in a schema more and more to pin these things down to make sure that your data is more strict. And in fact, that's one of the things I'll be talking about towards the end of the presentation. So anyway, so assume now we've got this fantastic graph. It's very rich. It has information in it that we can trust. There's a lot of information we can get out of it. It's all very well having that, but if you cannot get the information out of it, it's going to be a little bit pointless. So it's very, very important that all this good information that's in your graph can be searched for and therefore extracted in a meaningful way. And the reason why we'd actually want to search in the graph is obviously to get knowledge. That's what we want at the end of the day. And the idea is that we can get direct and indirect knowledge. So you can not only get information that you're seeking directly, but maybe can actually also get new insights. You may be searching for one thing, but in the course of doing that, you discover something else that you were not aware existed. So, like a serendipitous discovery. And yeah, so that's essentially what my take on a knowledge graph is, and how and why we build it up, and essentially what we want to get out of it at the end of the day. So just again to take a step back, a knowledge graph essentially provides a 360-degree view of any entity of interest. So these may be things like customers and things like that. Auxiliary entities, so these may be stores at which the customer perhaps did their shopping, and also customer reviews and things like that, things that basically support the main entities. And then also the processes that actually surround these. So maybe this is how the various fulfillment processes worked, or how the shipping worked out, or delivery and things like that. And to take even a further step back, essentially, if you really want to summarize what knowledge graphs should do and what their value is, essentially is they give answers about things it knows about. And of course, this means that the better the knowledge graph is, or the richer it is, the more it can give answers to. And very importantly, also explain how and why the answer was returned. And the great thing about this is that you can actually see what other facts led to this being the answer. Why was this the case, right? And this is something you can very easily get from the context and structure. And this, again, is something that we get with a graph. And just to really emphasize this, they must be searchable. And as I say, much more about this later. Right, so the next couple of slides are a bit more about how we envisage knowledge graphs working in Neo4j. So there's quite actually a lot going on in this slide, but if you would like to, I'd like to focus on the AI workflow loops. That's in the leftmost part of the diagram. And essentially what's happening here is, I'll just walk you through a process very quickly. Imagine we have a developer right on the left-hand side building a system. So this could be something like a recommendation system. And the system goes into production and all is well and good. And the system is being used. And as it gets used more and more, it essentially gets, for want of better words, thirsty for more data. It's the idea that adding more data to the graph, which powers this application, would actually be a good thing. And then the way this is done, and this is the idea of the graph platform idea I was talking to you about earlier, is that a lot of the information out of that application, as well as other applications within the enterprise, get put into a data lake or a data warehouse. And then the idea is that we actually have people like data scientists and business analysts actually going through this data and coming up with new algorithms, for example. So the need for these new algorithms are triggered because of the rich data coming from the recommendations app. Anyway, then the data algorithms, if you can imagine, bring up even more data and more good things that would actually be good to add back to that original graph that's used for the application. So imagine then that's now fed back into the graph, the algorithms plus the new data that it brings to bear. And basically you can then see it's a feedback loop essentially. As the application gets used more and more data is generated, which means the data scientists are motivated and triggered to produce and look at more algorithms, which in themselves go back into enriching the application. So over time, this graph gets imbued with extra intelligence. And generally now looking on the right-hand side of the screen, across the enterprise, obviously other people would also have a need for this knowledge to get back to them somehow. And essentially the idea is hopefully that better decisions are made based on this knowledge. So I'm going to just walk you through an example that probably a lot of you have come across, and that's certainly very prevalent in these days, is we have here two sets of fairly disparate information. So on the left-hand side, we have information about products. So it's very much product-centric. We have a catalog, we have purchases, all that sort of thing. And then on the right-hand side, we've got pretty much the customer journey post-purchasing something. And while all of these bits of information are in silos, it's actually very hard to obtain information spanning the entire universe of this particular domain. So for example, we can't answer questions like, why did a customer buy something? Was there something else they're looking at the same time? Are they likely to return? All these sorts of things. It's very hard to actually get a sense of what's going on because of the fragmentation of the data. So the temptation may be, and certainly this is what actually, it does work to a certain extent and has obviously been the status quo for quite a few decades, is to pull out all this information from these various databases into a data warehouse or a data lake. And the idea then is that you've got this pool of data, and the idea is then using a core set of tools. So this is Hadoop, Spark, those sorts of things, to write business intelligence apps that to consume that data and then to obviously spit out useful information. And as I mentioned, this is actually rather good up to a point. However, you may come across a couple of stumbling blocks, one of them being that a lot of the data, especially nowadays, may be rather unstructured. So it's kind of hard to, in this sea of data, pin down what the entities of interest are and obviously what their connections of interest are. And the second facet is that this process may also be quite slow, which means that what you don't do is you don't get the information in real time. So you've lost that operational flavor to it. So anyway, the format, to summarize, may not be very suitable for putting into action, and there's no way of actually drawing out actionable info in real time and real-time insights as well. So the solution to this, we think, or maybe one of the solutions to this, is actually the knowledge graph story, and we are seeing much more of this actually happening amongst our various customers, is that essentially relevant data is taken out of each of the silos. So maybe you take out some of the purchasing information that you deem relevant, some of the product catalog information, etc., etc. You take it out of each of their silos and you materialize it as graphs. And then these graphs are essentially joined into one large super graph. And you can actually see that in the top half of the diagram. So what we've actually done here is stitched together the facets or the important entities and connections of each silo. And this essentially is what our platform allows you to do very easily. So for instance, we actually do provide the capability and tooling to extract relational data out of a relational database. And we provide various ways to allow you to define how that data in tables is manifested as entities and connections. We also have a similar thing for CSV files as well. So anyway, owing to the platform providing the wherewithal to draw your data up into the graph, you're actually able to, as I say, materialize entities you're interested in and any interesting connections, and you end up with this larger graph that essentially provides you now with a really great cross-sectional view of the enterprise. What you can now do is query this graph in real time, and this basically means you're going back now into that operational mindset. So I'll just walk you through very quickly through a slightly different point of view, so just with an example. So as you can see in here, we've got three very different graphs. This is talking now more about the stitching together or joining together of information. So we have on the left a customer graph, we've got a product graph and a supply graph. And the idea is generally just to actually meld it all into one super graph. So what we now actually have is no longer a bunch of graphs, but we rather have a knowledge graph for that particular organization. And the idea is that this data now can get enriched over time. And that because of this joined up nature, right, where we've joined up customers, products, supply graph, etc., all of this information, we can actually possibly see how to enrich this graph even more over and above what was basically there in the first place. So for example, information that you can find in the left-hand side of the graph could actually be used to provide more information on the right-hand side. So this leads to you perhaps being able to add more information that would not have been obvious to add if that's still been in their original data silos. So we can actually, for instance, identify and materialize different types of customers, for example. By that I mean basically identifying different segments of the market, things like that. We could also perhaps have a notion of, bad weather alerts relating to delivery of items. So say there's a dreadful storm coming on the way and we can see that a number of our customers live in that area. We can actually forewarn them, look, we won't unfortunately be able to deliver your widget by the time we initially said we would. You're going to have to wait a bit. And I think, you know, being more responsive to these alerts and increasing the level of customer service in that way can only ever be a very good thing. So other things you can do, for example, is because you're enriching your graph with customer information, you can actually have all these extra auxiliary applications sitting around your knowledge graph. And what you can, for example, also do is record normal buying patterns for a customer. So that if you start seeing anomalies, for example, you may start to wonder, you know, what's going on there? You know, is there's some fraudulent activity going on? Has there been maybe some cybercrime going on? So all these things can actually now be done. So essentially the idea is that provided that we actually have a searchable and consistent and detailed intelligent repository, the idea is that actually this will serve corporations doing this, and essentially the idea is that such corporations will actually always be one step ahead of the competition. And in a nutshell, what's required to actually get there essentially is what I was alluding to earlier, is that actually over time you enrich more and more and more through any means that you can see, including using information from other parts of the enterprise, through to graph algorithms, through to analysis, etc. Cause that to enrich your graph, and also to ensure that there is a way of actually getting information out of the graph. Just very quickly to end off this section is we also just peeking a bit into the future. We foresee that a knowledge graph could end up being the foundation for AI-related activities in the future. So, for example, this would include data scientists developing new algorithms to utilize the graph. So obviously there's a huge pool already of theoretical knowledge about graph algorithms and how to execute them efficiently. But obviously, because this area is now getting quite hot, even more resources are being put into this to research even more interesting ways of undertaking these sorts of algorithms. The idea as well is that as the graph gets richer, the data scientists can derive new insights to enrich the graph even more. So, for example, if you use a deep neural network, you could explain how, when, and precisely where decision-making occurred, and also materialize that information. And then the idea is that could be exposed to future similar searches. So things are essentially learning over time. And if you recall earlier on, I was saying that your graph gets more truth, and this basically links back to that. So you can actually record, how various things were derived, or how they're caused to come into being, or why they were caused to come into being. This actually adds to the truth of your graph. So I'm just going to walk you through a few ways of actually how you can enrich your graph. And I'm going to begin with something probably most of you have heard of, and that's natural language processing. So essentially this is understanding human language. And the idea is that a block of text would come in, and this would be parsed using various parser libraries to extract entities and various attributes associated with these entities. So maybe we can actually, for example, in some sentence, get the idea that this thing called Daniel Craig is actually not a thing, he's actually a person. And moreover, because of other various words or clauses that sit in that sentence or in that paragraph in which he's mentioned, we can also infer that he's not just a person, but he's also an actor. To continue a little bit with that, there are actually a couple of side topics, I suppose you could call them, related to NLP. And in fact, there's a lot of academic research going into here at the moment. So this was certainly not the case about 10 years ago, but because of this becoming quite a hot topic, certainly a lot of researchers have taken up the baton. So entity disambiguation, and this is really, really difficult. How do you actually tell apart Amazon the rainforest versus Amazon the online store versus Amazon the tribe of warrior women, if I recall correctly? How do you tell these apart? It's actually much more difficult than you'd think. It's usually from the context, but it's never as simple as it sounds. Also, another facet is sentiment analysis, and that's trying to identify from a statement what's perhaps being inferred or what's not being said directly but is being meant. Things like polarizing statements, negative statements very much, that sort of thing. So I've sort of skirted around this a bit indirectly, and this is what I was meaning about when I was talking about the truth of data, and that's around the area of provenance and lineage. This is, again, I come from an academic background. This is certainly being researched a lot lately. And it's also around, what actually brought it to the fore is, particularly in scientific communities, is the need now to actually provide traceability. So it's all very well providing results that have been discovered, but that's no longer enough. You now need to be able to show how you derived those results. So what was the raw data? What processes and experiments did you undertake on that data? What were the derivations you made on that data? How did you actually eventually end up with your conclusion? So this all needs to be traced through. So essentially this is down to being able to undertake repeatable experiments. Anyway, so this may have, obviously, as I say, come from that particular domain, but this is certainly something that would be very valuable in an industrial context as well. And from this you can actually see that auxiliary functions such as snapshotting graphs and versioning graphs would actually play into this a lot. In fact, I'll talk about that a bit more later. Right, so inferencing and actually deriving new facts from machine learning and algorithms. So this is actually, I've obviously provided a couple of links as you can see on the screen. These are free to use out of the box, so I do urge you to actually have a look. So the first thing is actually around 450 procedures and functions, and I had a look yesterday, and I believe that was the number. And essentially, these are a whole bunch of excellent utilities that help you with everything from data integration, various graph algorithms, data conversions, etc. So everything that people have stumbled across in the past, they're actually now enriched or encapsulated into very easy to use procedures and functions. So lots of documentation around there as well. So I do urge you to have a look. The second facet is actually our graph algorithms library. And again, this is free to use. And because we've actually linked with various academic institutions and also industrial institutions whose speciality is in this sort of thing, we actually have ensured that these are very highly parallelized and therefore run very super efficiently. And you've got everything there from centralities, PageRank, betweenness, community detection, pathfinding, etc. So I'd be very surprised if you didn't find what you were looking for in that list. Also to mention both these areas are being enriched constantly over time as well. So new things are always being added. Things are being made faster as we learn new things. So another way of actually enriching the data through the inference or derivation of new facts is something called the deductive method. So I'm not sure if any of you here are from the knowledge base or ontological world. So certainly I'm talking about RDF and Sparkle and things like that. That's actually to derive new facts through actually using rules. So for example, I've just sketched out an example down there. So the idea is let's make node X more meaningful. All right, so assume node X has a person label, and also it's got an outgoing teachers relationship. What we can then encode in here is that node X should not just be a person, but they can also be a teacher. And as you can see, this essentially makes node X much more finely described. And as you can imagine, there are all sorts of variations on these sorts of simple rules, and these things also get quite complicated as well. But certainly this is another area that is well worth looking into. So continuing with that, you actually can also use external data sources to obtain new facts. So for example, and they've noted ConceptNet and WordNet. So for example, WordNet in particular contains lots of information about synonyms and very similarly meant terms. So say for example you want to treat a teacher in the same way as you treat a lecturer, and you can reflect this in your knowledge graphs, that when teacher is searched for, you can also get information about lecturers as well, because maybe the user won't be aware of the fact that there's this distinction in the graph. They're just after anyone who teaches, and obviously that encompasses both of these terms. So it's all very domain specific, obviously. So yeah. So also if you're not sure of your graph and not sure of what the rules are, you can actually, as I say, hook into these external sources. I think there's also one for geographic information as well. So that's also something to potentially look at. Right, so this is the final section of the talk, and it's all going to be about graph-based search. So I'm hoping that most of you know what Cypher is. So I'll just very briefly give an introduction for those of you who don't. And this essentially is our graph query language. It was developed by us, by Neo4j, but it's no longer actually a Neo4j only thing. So we actually, a couple of years ago, opened it up because we actually would like other graph vendors to also use Cypher. We think it's such a fantastic language. It should really be the language that people use when searching in graphs. Just like SQL is great for searching in relational data, we think Cypher should be the language to use when getting things out of your graph. And the idea around that is it's declarative, so it's very much like SQL. You state what you want, not how to get it. And the beating heart of Cypher is the pattern matching part of it. And this essentially is just how to transcribe patterns in your data and telling your getting data that matches your pattern out of the graph. So what we actually have there, it's a full language. So we have DQL for reading data, and that's actually what I'll be focusing on in this section. We also have DML for actually mutating the data, and also DDL for creating constraints and indexes. But as I said, I'll only focus on the first bit. And what Cypher gives you, and you may be thinking, those of you coming from the SQL world, what's special about it apart, say, from the pattern matching aspect? It also actually allows you to very easily do recursive querying. And this certainly is something you can do in SQL, but not very easily. So essentially what you can do is things like transitive closure. And in fact, there's more about that in the next slide. Related to that is actually a variable length relationship chains, and also the ability, which is very different and plays very much into the knowledge graph story, is the ability to not just return properties or nodes. It's actually the ability to return whole paths. And as I said to you before, this is actually a really useful thing to do to see why a particular answer was returned. You can actually see exactly what the path was that led to that answer being the answer it is. So just to show very graphically what's actually going on. So what we have is the match clause, and this is the clause that essentially expects a pattern, and the pattern then is given by the rest of the query there. So we actually have a node pattern, and the node pattern is actually the pattern that's enclosed in the round parentheses. So there we actually see that we're looking for a node with a label of person. Furthermore, we're also expecting that this particular node has a name property and that the value of that name property is Dan. Then we're going on to something we call a relationship pattern, and that's in the gray text there. And we're actually saying that that node has an outgoing relationship. So you can see the arrows pointing outwards. So it's going from Dan to the other node. And furthermore, that relationship has a type of loves. Now, it could be that relationship, there are relationships in the graph with type loves and that also have properties, but because we haven't specified any property predicates in this pattern, that's not taken into consideration. And then just to end off with, on the right-hand side, we actually are then searching for any nodes that are connected in that way. And because no information is given in that node, so all we're doing is just assigning it a variable. We're not specifying a label it needs to adhere to or a property. It's just going to return any node. So it will return people, it will return dogs, cats, etc., anyone whom Dan loves. And then the actual return statement pretty much is analogous to the SQL select statement, and that essentially just specifies the data to be returned. So in this particular instance, we're just going to return all the node information matching whom. So for example, what this would return to you is the labels of the node, as well as all properties of the node. But we could have also said whom.name, and then what they would have returned is the name value of all nodes returned that fit that pattern. So there's quite a lot of detail going on here, so I'll just go through this very, very quickly. So as described, we have the beating heart of Cypher, which is the match pattern, and in there we actually have transcribed a pattern. We also have, like SQL does pretty much, we have filtering with predicates. So we have the where clause and things like that. We can project data values and expressions using the return clause. And just like SQL, again, we have things like ordering and also things like slicing and things like that. Going then to the middle of the screen, this is where it gets very much more Cypher in a way. And this is this variable length relationship pattern. So remember earlier I was telling you about transitive closure. So if you look at that first query, match me, friend, star, foe, what that essentially will tell you is traverse from me, some me node, one or more friend relationships. What this will actually do is it will traverse for as many friend relationship types as there are in the graph. So assuming the node me starts at somebody called Dan, it will then go to his friend, his friend's friend, his friend's friend, etc., 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 until essentially all the nodes related in that way have been returned. And that's essentially transitive closure. There's also a way of bounding transitive closure, and that's exemplified in the second example, where we're actually specifying in there traverse 2 to 4 friend relationships. So that will traverse all friends that are 2 friend relationships away, 3 friend relationships away, 4 friend relationships away, and then it will stop, basically. So this is actually a way of limiting the results returned. So you can imagine using these structures in particular for tree data or like a department. You know, when you've got departments containing departments, that sort of story. So you can actually extract a whole subtree out of there by using things like that. Very important to note is that Cypher today takes as input a property graph and it outputs a table. So if you're wondering what these what the return statement actually returns to you, it essentially is a table. It will be usual columns and rows. But a bit more about that in a moment. And then the other very cool thing about Cypher is the path binding, where actually you can return paths. So if you look at the very last query towards the bottom, you have something called match p equals and then some pattern. And in there actually we can see that we can, so this is something I hadn't mentioned, you can actually chain together as many nodes and relationships as you like. So it doesn't need to just be node, relationship, node, and that's it. You can actually go on for a bit further. So in there we have got A that represents a node with a relationship through to an anonymous node. That's the one, the first empty parentheses. Then going out with a to relationship, and so on and so on and so on. So you can actually chain it quite in a quite lengthy way. What's then returned by P is all paths that match this particular pattern. And what this will actually consist of will be, in the order that is described, all the nodes followed by their relationships. And for each node and for each relationship, all of the other information will be materialized in your table. So you'll see for all the nodes, all the labels and properties, and for all the relationships, you'll see the type, as well as any properties that are associated with that relationship. And as I said before, this particular facility tells you why the answer was returned. So it's going back to the context that a knowledge graph can give you. So you don't just get an answer, you can actually see, you can track back to why was that answer given? What was the path between where I started from and through to where I ended up? So I'm now going to walk you through what the particular group I work in has been working on. So these are extensions to Cypher, and there are about 4 of them, if I recall correctly. And the first one is actually talking about multiple graphs and query composition. And don't be worried, I'm going to explain precisely what is meant by these terms. So as I mentioned before, Cypher today is essentially a single graph model. So what happens is you basically come into Neo4j and you start writing a Cypher query, and what it will query is a single implicit graph. And I say implicit is because this graph doesn't have a name, it's just there, it's the graph. Anyway, the idea is to actually move that away from this single graph model through to a multiple graphs model, right? So where we actually have the property graph database contains multiple graphs. And so you may actually be wondering now, okay, that's quite a change. Why is that actually a good thing? So the implications of actually having this is the following. We'd actually accept multiple graphs as well as a table as input. And you may be wondering, why on earth, why would we want a table as input? We've actually seen in many potential use cases and through conversations with customers, especially in the more complex sectors, that actually having an input table can be very useful as a driving mechanism for generating graphs, right? So the idea is, in this brave new world, not only would we return a table as we do today, but also we'd return graphs. So that's probably something that maybe many of you who've used Neo4j have always wondered. It's great that, I'm able to query my graph, but I can only ever get the data out as a table. That's maybe a bit annoying. Well, in this new world, we'd actually be able to return the graph as well. And not just one graph, but also multiple graphs, depending on what you need. What this actually means is that this would give you the facility to do many, many things with this. And that one of them is actually to create new graphs on the fly, either from scratch or actually from existing graphs. Maybe you want to, remember how I was talking earlier on about how you'd be looking at your customer data and just drawing out the subset of entities you're interested in. So basically, just to draw out a subgraph. You can then also combine and transform graphs from multiple sources. You can also have things such as views. This is a very good way to actually abstract logic. And this actually feeds directly into the subquery support as well. A number of other things, snapshots, rolling up, drilling down operations, all those sort of business intelligence type operations. But also things like access control, which is certainly very, very important for many, many, many businesses. So this is all about security, right? So you don't want your knowledge graph, for instance, which obviously will probably have some sensitive information, being accessible to anybody within your company. You obviously want to maybe limit this to only people with correct clearance. And then the idea around this is you'd actually create a view over that. I've actually noticed I'm going quite short on time, so I may just need to step up the pace a bit. The adjunct to this is something called query composition. So this is possibly one of those tricky terms. So what I've actually tried to do is to describe what we actually mean by that. And all it basically means is that the output of one query can be used as an input to another. So essentially, if a query can return a graph and a query takes as input a graph, you actually have composition. And you can actually see in the image on the right-hand side that The first query takes as input 2 graphs and a table, and it forms then the blue graph in the middle, and that's actually formed by some logic where the first 2 graphs in the table were somehow combined. It's fed then through to another part of to another query, which then spits out a final graph. Maybe it's an aggregated graph or something like that, as well as a table. And the idea around here is that actually you can reuse logic. You can actually replace parts of this pipeline, if you like, without affecting other parts. And you can actually, in this way, build very complex workflows. The next flavor is actually something called complex path patterns. So for those of you who are familiar with regular expressions, so I've actually just done a quick little summary up in the top left. This actually comes from academia again, something called regular path queries, where you can actually specify a path by means of a regular expression over the relationship types. So I've just given you a quick example down there. So what this actually would do is it would follow a knows relationship and then one or more of the following: either likes followed by eats or drinks. So that's basically the idea of this particular function. Anyway, that's actually was research undertaken on classic graphs, i.e. graphs without properties. So in our world, we actually need to make this a bit more complex for it to become useful. So in Cypher, we're calling these path pattern queries. And the idea is that we not only look at the relationship types of the path you're interested in, but also we're looking at the node labels of the nodes along that path. Maybe we want to exclude all intermediate nodes that have, say, a dog label or something like that, and also to introspect properties along nodes and relationships along that path. And as a final flourish, we also would be looking at actually being able to specify cost for paths as well. Maybe this would be by the length of the path, or it would be some cost function that the user would express. Much more information actually is available in that link down at the bottom. And here's an example actually. So in here we'd actually, and I do actually must point out this is a very much illustrative syntax only. This is by no means the final thing. So up on the top we declare a path pattern. And you can actually see there's a predicate on there, and it's just a friend relationship between 2 nodes. The idea then is in the match clause, what you do is you'd actually insert this path pattern, and that's indicated in the orange font, where that occurs 1 or more times. And then we go on from there. Very briefly, so probably those of you who are familiar with Cypher today, it's actually, we use something called relationship isomorphism. That's a hugely horribly tongue-twisting term, meaning that no relationships are repeated in any one pattern. So this particular example is actually showing, for example, that when we navigate out from Jack, so we go to Anne, then we go to Tom, we actually will then not backtrack. So for example, R1 and R2 cannot bind to the same relationship within the same pattern. So essentially everything ends at Tom and only Tom is returned. And we actually have found that this has been, this approach was actually never really thought about. It was just the way it was developed, and this is just how things have happened. It's actually proven to be quite useful in that customers get the results they expect to find. But it has actually come to our attention that sometimes you may actually want to have repeated relationships being allowed. So the idea is that we'd actually be able to allow for queries to be configured to use whichever one of these morphisms are of use. So as I said, relationship isomorphism is what we have today, but you can also maybe specify that you want homomorphic pattern matching. That is where the same nodes and same relationships can occur more than once in a path, but also maybe people want to go more restrictive, that also we don't allow the same node to appear in a path more than once. That's even more restrictive than what we have today. A couple more things as well. We actually would be looking at quantifying the pattern, so seeing how many matches are actually returned. So, maybe you just want to see, are these 2 things actually connected at all, like an existential path search, or maybe you just want to get all of the matches. And then also there'd be some length restrictions, such as shortest, and this is what I was mentioning earlier as well. Consider only shortest path, and that's determined by the length of the path, but also maybe cheapest, and that's by that due to that cost function I spoke about earlier. Unrestricted would just be, give me everything. And finally, just to end up with the schema. So remember how earlier I was talking about the fact that as you enrich your knowledge graph more and more over time, you may actually find that you want to start locking things down because you want to ensure that your data quality remains high and in fact continues to go higher, we actually are looking at enriching our schema model much more. So what we actually are looking at, and this is just some examples, there are many more, is things like endpoint requirements. So we'd actually have the requirement that say an owns relationship can only ever end at a node labeled with either vehicle or building. So it can't ever end at, say, shopping center or something like that. And also cardinality constraints. So for example, we're saying that between any two person labeled nodes, you can have 0, 1, 2, or 3 nodes relationships, but not more than that. And as I said, there are a couple of other things we're looking at as well. But yeah, with that, I should like to thank you for your attention. And I think maybe we have time perhaps for one question. So we've gone over a bit.
Yeah, not a problem. Thank you very much, Petra, for the presentation. So if you do have any questions for Petra, please just type those out in the questions box. So we have one here. When you talked about the extensions, you had mentioned a graph and a relational table can coexist. So do you know of any converter tools to kind of translate a relational database to a graph database or vice versa?
So I'm not aware of the vice versa. So I'm not aware of how you translate graph data into relational form, but certainly we do have tools. It's called our ETL tool, which allows you to actually look at your relational schema. So you'd obviously see your bunch of tables and your keys and everything. And in there you could actually pick out what information from those tables would form your nodes, and also what columns maybe say would actually also be the properties for those nodes, and also what the name should be for the label that you'd assign to those nodes. And the same goes for relationships. We actually do have an ETL tool, and also we have a tool that allows you to load CSV as well. And through the use of Cypher for the loading of CSV files, you can very atomically and at a fine granular level specify what columns in your CSV file will be the nodes, what will be the properties of those nodes, and how they'll be related to other data within that spreadsheet, within the CSV file.
Okay. Can you compare kind of master data management with knowledge graph? Is that a similar use case, or how is it different?
Yes, I think a master data management is probably knowledge graphs -1 in a way, in that master data management, I think first of all it arose from a different, it arose very much from a business context, and that was just basically the way you actually are bringing data out of your silo and stitching it up into kind of the one super graph. The knowledge graph then takes that one step further in terms of the enrichment. It's actually using things maybe not like NLP, those deductive rules, graph algorithms to further enrich that knowledge graph over and above what was actually initially sucked up or extracted out of the original data silos.